hear anyone.
Can you hear us? Can you hear me? Don't think so.
Okay, now I think I hear.
All set? Nice.
Okay.
Hey, Johan.
Hello.
Hey. Looks like Jeff might have been having some technical difficulties. Hey, Emanuel.
Hey.
UME, what is that? Swept back cat. What's up?
How's it going?
Good.
Hey, I'm just calling it from a post here while I'm waiting for my vehicle to get repaired. So I'm going in from a call from the phone for the time being. Hopefully, I'll make the rest of the call from my computer.
All right. No worries. It was a bit hard to hear you, but you're not presenting, so that's all right. I think you're just on the phone, probably.
Yeah, it's a bit of a loud cafe, so I'll stay muted for the most part. But happy to listen in.
Cool. Yeah, no worries. We'll just give it a few more minutes here. See who else trickles in. Hey, Zargham. Welcome.
Thank you much. I guess I will put myself on screen. Hey, I think we're gonna end up waiting a few minutes for people to roll in, but yeah,
Yep.
I'm gonna actually use the restroom real quick because I've been in a chain of meetings, as
Back
I'm
to
sure you
backs.
guys have all.
Yeah, no worries. We're gonna wait a few minutes for sure.
I'll be right back.
Sounds good. BK. So at Backcat, actually, how'd you hear about the call? Were you in the labs channel or Oh no, you were in the LTF group, right?
Yeah. Yeah.
Ah, okay. Awesome. Very cool.
And
So,
my name's actually Nick.
okay.
Yeah. So
Wouldn't have guessed. But good to know. Okay, we could get started here actually. We just usually go around with like a quick background intro for everyone that's joined anyways, so it'll leave a few minutes for people to trickle into if they're still running late. Cool. So yeah, we have both of our presenters, Zargham and Emanuel here. Thanks for making it. Super cool topics on the agenda for today: the cadCAD tech spec and the Julia implementation of cadCAD. So super exciting. I can start with the intro. So my name's Peter. I've been organizing the cadCAD community calls for the last few months. Kind of got roped in with Jeff and Jess to help out, and it's been really cool. We've had some awesome presentations for the last few months, really, and all the recordings are available if you want to check them out later. But yeah, other than the cadCAD call, also involved in the TEC, been around the labs channel a bit, helping out with the Common Stack on a few projects here and there, and recently started also working with Angela at the Token Engineering Academy to help run some of the research programs. So yeah, token engineering is awesome. Glad you're all here. I'll pass it to Nick.
Hey, so my name's Nicholas, and or Nick, and I have a background with computer science and mathematics. I'm currently still a student. I'm about to enter my last year. I got introduced to LTF or long tail financial, and so that's kind of my intro into this world of token engineering and all the many facets that come with that. So far, I've been finding it pretty cool. Slowly getting involved with projects in the TEC. I know that I started to help with Token Spice about 2 weeks ago. I started trying to understand what was happening there, so I could be more involved with that later on. Otherwise, yeah, I'm just kind of excited to see what this call has in store for cadCAD. With that, I'll pass it to BK.
BK, not sure we can hear you.
Oh, sorry.
Oh, yeah, there we go.
Thanks, Nicholas and Peter. Hi, everyone. My name is BK, and I have a background in electronics and data science. And I too work in LTF along with Nicholas. And I was introduced to token engineering, and we have been using cadCAD for about since I joined, and it would be great to see the updates in this call. And I'll pass it to Johan.
Johan actually just messaged me, said his mic's not working.
Oh, okay.
But you can pass it elsewhere.
I'll pass to Austin.
My background's in physics and music. Pretty new to the token engineering space, and I just checking out the cadCAD bootcamp last week or 2 weeks ago. Yeah, so I'm excited to see what's new. I don't know who else has gone.
Very cool. We can pass it to Octopus.
Hello, can you hear me?
Yep.
I'm Octopus. I am a mathematician and I like to write code, but I'm always eager to learn more about that. I've done the cadCAD bootcamp and I am looking to make the transition to actually using cadCAD as a tool rather than just having a theoretical understanding of it. I actually can't see the participant list, so
Yeah, no worries. Jeff is, I think, in a loud cafe, so maybe we'll skip him, but I think most of us know Jeff anyway, so that's okay. And then, yeah, we can jump into the two presenters. Z, do you want to give a quick background?
Sure. Yeah, I mean, I'm Z. So, cadCAD comes from the fact that I am like a systems engineer and algorithm designer by like formal training, PhD work, etc. But in school, I'm sure many of you have used MATLAB, and I use MATLAB for lots of things, mostly modeling and analyzing algorithms in complex dynamical systems. And of course, then I'm using Python and hacking things from scratch. And some years ago, I got fed up with that and kind of came up with the idea of building a framework for doing complex dynamical systems in Python, and kind of cadCAD spawned out of that. I do use it for lots of quote unquote token engineering, but I actually like to clarify that cadCAD is more of a data science tool than a tokens or Web3 tool. It's about representing mathematical objects and analyzing the properties of those mathematical objects. Those particular mathematical objects that we work with tend to relate structure and behavior, and so, or like composition between decision making and the field of action or the consequences of those decision making. And I'll get into that a bit in my presentation. But I think maybe for Octopus' sake, I'll point out that today's call is probably going to be a little on the math heavy side, which is good because I'm stoked that you're here. It's bad maybe towards the end of focusing on practical application. Yeah, I don't know, Emanuel, do you want to do your intro?
Yeah, sure. But I think Johan didn't introduce himself. Do you want to?
Yeah, he told me he was having mic issues, but we can try again if he... Give him a second,
Okay.
maybe.
So,
yeah, go for it.
If he wants to talk, let us know.
Yep.
So my name is Emanuel. I am a research engineer at Block.Science. I am a physicist by training, actually finishing my training. It's very close to finish. And I've been responsible for more like software engineering aspects of cadCAD, and mainly focusing on performance. So I'll talk about that in a minute when I talk about the Joule implementation. And well, I'm going to save it for when I talk about the engine. So yeah, basically that.
Cool. Sounds good. Then yeah. So do you guys have a preference who jumps in first? Z or Emanuel?
I'm gonna go first.
Cool.
The agenda is this. I'm gonna go over a little bit about what generalized dynamical systems are. Then Emanuel and I will kind of co-present the cadCAD specification and the recent updates to the cadCAD specification. Then Emanuel is gonna go into sort of performance and some of the software engineering aspects. That's what we've got for an agenda.
Perfect. I'll let you have the floor then.
Going to Google. Let's see, present, okay, come back to Discord, select the right screen to share, because I totally know how to do that, I swear, god damn it, entire screen, let's just do that, then I can switch to this one. Can you see my screen?
Yep, all set.
Alright, so, and this is going to be kind of annoying for many people maybe, but I'm going to quickly review what a dynamical system is. So a dynamical system is a way of describing the way something changes. So, we think of, let's just say, data structures as a way of reasoning about state. They represent a snapshot of a thing. But when you declare a dynamical system, you're not just declaring the state space or the state of the thing, you're declaring how it changes. They generally come in two forms, discrete or continuous. There's more to deal with that are mixtures and things get complicated and messy, but for simplicity, we're going to talk about the canonical forms. Ones where you describe the differential, which is where derivatives and integrals are descriptions of these sort of differential operations. You know what, I'm not going to go into calculus stuff, but suffice it to say that you describe the laws of motion or the rules about how things change.
And in computer systems, we generally work with discrete time systems, just meaning that you have a value and then you have a map that gives you a new value. In engineering, we generally work with vectors and matrices to represent these things, but in a more general sort of social and economic systems, or really any physical system setting, you start to have to deal with more richness in interrelationships that can easily or legibly be encoded in directly in matrix and vectors, and so we'll be working with generalized dynamical systems. And basically, all a generalized dynamical system does is kind of concede some of the basics that are attached to dynamical systems over, matrices and vectors and stuff. And we just say, look, now my state is a general data record. It's just got some schema, which we can think of as the state space, and it's got records, which we can think of as instances or snapshots of the system at a point in time. But now our dynamics represent the way that record changes over time. And you'll see in some of our models from cadCAD that are out there, we often have networks. We can have mixtures of networks and dictionaries and basically whatever structure we wish to impose on our representation of the world. And then our simulation is taking the thing and applying a map onto the same space and getting another instance of that kind of thing. And we build up that structure, and that's our simulation. One other thing in cadCAD that's super important, at least in my opinion, is that we have further characterized the difference between laws of motion, or like the rules about how a system changes when you act on it, and the choices about what actions to take. This is super relevant for crypto, because in crypto, all of the laws of motion are really hard. Like, if you try to do a double spend, it just reverts, it fails. So you can actually codify the set of admissible or feasible actions or inputs, and in fact, it's a function of the current state of the system. In other words, I can only spend stuff that I have. This generalizes a lot to much richer mechanisms in crypto, and actually is also equivalent to how we understand the laws of physics. Like, you can understand the consequences of exerting a force on a particular mechanism if you understand the physics that exerting those forces sort of is governed by. Literally, I can push on a lever and know the consequences because I know my mechanics. And so this is the level at which the learnings from physical sciences are most relevant to social and economic systems, is where we say, we all know if you do this, this will happen. I don't know what you'll do with that, but we don't have to worry about disagreeing on what will happen if you do. And that results in dynamical systems that have a really interesting flavor. I guess these slides, I'm going to run through them quickly, kind of diving in on the criticality of the state. This is our description. In cadCAD, our state objects are explicit files. We have a lot of things that we put in there, but they just represent what we care about looking at. It's our data. Actions, however, they're slightly richer than just, the new state is a function of the old state. We have this separation between the current state, the input, which is the previous state, and the input, which is an action that is taken. And sort of kind of revisit the concept I was just explaining. An action is drawn from an admissible set, the set of things you can do. If you have an engineering or control system, signal processing, electronics kind of background, these inputs appear as sort of input ports, they're actuators. The stuff that you are able to do, or the affordances of the mechanism, is the set of admissible actions. And again, in crypto, the easiest way to describe this is that a send is an instance of a U of T, and in particular, a send from one address to another is a specific instance of an admissible action, and that admissible action is constrained in a state-dependent way by the balance of the sender. And the exact laws of motion that dictate the state change are encoded in the protocol, such that if you did that, you know what would happen. And so this is sort of crux or critical. Yep. What's up?
Could I offer a comment?
Yeah.
Would it be like the actions are like keys on a keyboard that you might press or something like that?
Yeah, that's a reasonable way to think about it, and you have an understanding of the consequences of pressing that key. Just because you know doesn't mean you press it, but you would expect that if I press the key or if you press the key, the same thing would happen. Or I guess up to the point of control. Like you press your key on your keyboard dependent on the state of your computer. I press my key on my computer dependent on the state of, the application in front of me. But like there's still a symmetry in that up to the state that is the local state to you or the local state to me. Does that make sense?
Yes, if you would entertain a question. My other question is, why did you say earlier the mapping didn't have to be a function?
It just has to be a map. I guess this is where things get. I think I say it was a function just of x. It's a function of yeah. Okay, let me roll this back. It does not need to be a function f of x like this. It's almost certainly a function f of x comma u. So it's a function of the domain state cross admissible action space. And we'll actually hit this a little bit more in the spec. Yeah, and the definitions, getting into the functional analysis versus more general map operators is not something that I'm even prepared to do because I have to look at my references in order to not screw that up.
No worries. I thought it might be an important. I thought it might be an important distinction. It sounds like it's not terribly important as a distinction.
Yeah, I don't think so, at least not at this stage. I think there are some circumstances under which it might be important, though, because I'm using this function I'm using it somewhat liberally here in the sense that I'm comfortable with anything with the right domain and codomain, and I'm not making really strong claims beyond that. I simply have to have a domain, which is the current state cross or some subset or some subspace of the current state and some action space. And so one of the main things that we're digging at here, though, is that the action space or the admissible action space is itself state dependent. And so this little cartoon here basically says, okay, well, if the current state is xt minus 1, then the set of things that can happen lies in this u of xt minus 1. So you can select any one of these things, but once you do it, you might actually change this. So maybe as a result of that, new things are possible. But then maybe as a result of so now I pick something from this new set, and it's possible that this actually reduces the set of admissible actions, right? So there's a sort of there's a possibility of both expanding or shrinking the set of admissible actions depending on what the mechanisms are. So Jamshid made these slides, and their point here is just that there's a really critical state, which is sort of implied, or critical dependency of the state, which is the set of admissible actions itself. So when you're designing a mechanism, and in particular, this is what we often do with cadCAD, we don't just look at the consequences of the action, but actually the set of actions that one could take. It creates a kind of discrete differential inclusion. And it's that discrete differential inclusion that we tend to analyze when we're doing token engineering projects. Whether we realize it or not, we're running computational experiments to explore what can happen and the circumstances under which certain points are more likely than others. And so we tend to do this mathematical decomposition where we think of the action as its own policy or behavior. And that starts to line this back up with literature from both controls and economics. We end up with a closed loop system, a dynamical system, but a generalized dynamical system takes as an input some assumptions about behavior. And so while we can declare as token engineers, mechanism designers, engineers of any sort of physical system, the desired properties of our system, we can at best constrain the set of actions that are possible. not actually decide what actions actors will take. And in fact, if we did decide what actions actors would take, then we kind of lose our ability to I don't know, like think of this as a social or economic system. If you're deterministic about what one should do or must do, you've actually constrained it too much. And so this is maybe the touch point to the token engineering or the mechanism design element, is that when you're doing dynamic mechanism design or like dynamic analysis of dynamic games, you're structuring the field of play when you select the mechanisms f of x comma u and the domain, or the part of the domain for the actions, which is this method u of x. And so what we're going to do is jump into the cadCAD spec and look at how these concepts appear in the specification for cadCAD itself. And then we'll look at some of the software engineering aspects of implementing it. So I don't know if there are any questions. This is really the only slide that I need, but admittedly it's a little heavy and it's under current revision. So Jamshid and I are working on like a sort of short paper that is meant to finalize or formalize a bunch of these definitions. But you will notice, Octopus, that we, after much discussion, chose map over function, and some of that does come down to the formalities. I just can't really speak to them in real time.
I appreciate you talking about it.
Cool. So I think it makes sense for us to jump to spec, and I'm gonna let Emanuel present. We're gonna pull up the current version of the spec, which, just for understanding, the purpose of cadCAD was to enable this kind of mechanism design in these social and economic systems, and it's been developed and iterated on by people at Block.Science and beyond. But again, originally the motivation was to ensure that we could follow a kind of robust, almost civil engineering methodology for designing mechanisms. One where we respect the gap between, what we declare in our mechanism design and what happens accounting for user behavior. And so we're building a piece of software that allows or it facilitates that kind of analysis. And so the specification of cadCAD itself is actually not language specific, and it's about the features or the transition of the mathematical objects, generalized dynamical systems, into computational objects that we can evaluate and analyze and use as a tool. So I'd like to think of it as the bridge from math objects to computational objects, if that makes sense. Also, feel free to ask questions if anybody has any.
Just turn on my microphone here.
So Emanuel, you want to kick us off? Because, I mean, this document was a byproduct of, well, basically you helping me smash that, ramble into something implementable and reliably, verifiably implementable.
Yeah. So the thing I was going to say when I was presenting myself, and that I waited to say now, is that the Julia implementation of cadCAD, it was born with performance in mind, but it was also an opportunity to put to test a formal specification of what cadCAD is, like a language for encoding generalized dynamical systems, and there was a back and forth communication between the writing of the formal specification and then the programming of the Julia engine. So both things were done at the same time, with different paces, of course, because now that the math of the specification is somewhat figured out, there remains the more software engineering aspects of the engine to be ironed out, so that we can launch the Julia engine, right? So, as for the formal specification, so basically the formal specification of cadCAD is a set of definitions, right, that say what a cadCAD engine has to do and has to have inside of itself in order to be called a cadCAD engine. Because the concepts are the same, but the constructs will depend on the language. So if you use like a purely functional language like Haskell, of course the source code will look like very different from a Julia source code, although both source codes can like obey the same formal specification. So basically this is a guide, all right? So whenever someone else has a need to write a cadCAD engine that is different from the ones that we already have, or if someone has the need to extend the engine, because we're talking about open source software, right? If someone has the need to extend the engines that already exist, this formal specification can be consulted to see if it complies, if your engine complies with it. So basically, the formal specification says that there's a state, okay, and the state is a concept that when mathematically the state is composed of all the attributes of your simulation, of your model, and programmatically, from the computer science point of view, that state can vary from any language. For example, and I'm going to talk about that later. But basically, for example, just you guys can like put one foot on mathematics and another foot on the computer science. That state, like mathematically, is an object from a state space. Okay, so and from the point of view of computer science, on the Python implementation, that state is a dictionary. On the Julia implementation, that state is a struct. Okay, so things may change. So basically, we have initial state, all right, and that initial state belongs to a set of all possible states, all right, and the whole point of cadCAD, as Zargham discussed on the Generalized Dynamical System, is that we begin with the initial state, and then through a dynamics, that is, through a set of laws that are applied on that initial state, we build what we call a trajectory, all right? And the trajectory are consecutive states that all belong to that same state space, all right, that are built by applying those dynamical laws on top of the last state. Okay, so you guys can imagine that we have like a list of states. Each of the state was created based on the last state of the trajectory by applying some laws into it. Okay, so the set of all the laws that we apply on the last state is the dynamics of the simulation, right? And that final list of all the states of the simulation is the trajectory. That's basically what all this mathematics is talking about, okay? And when we talk about dynamics, we separate the laws that are like more non-deterministic, you know, if they are stochastic, we call them black box operators. And if we say that the laws are deterministic, we call them white box operators. Okay, so we make this distinction. And of course,
I'm going to just jump in on this a bit, because this is where, in this section, dynamics, this is where modeling happens. So like everything else, in a sense, is about the engine, but we have abstracted away all possible cadCAD models in this dynamics section. We've basically said that, and if you guys look at your cadCAD models, you'll see like a partial state update blocks file in the Python implementation. What that actually does is encode a sequence of maps h of x, where each one of those maps h of x decomposes into g and f. And furthermore, sometimes G is empty if the input is empty, but F is the laws of motion, or the physics in a sense, and G is the behavior or policy making of some kind, something we know that we don't know. F is stuff that we know that we know, G is the stuff that we know that we don't know, and although we change both of them, we change them for different reasons. We're sort of designing F generally, whereas we are sort of modeling or making assumptions about G generally. It's a bit of a heuristic for thinking about how to build models, but the cool thing about this is that all cadCAD models are actually, dynamical systems with, state maps h of x, which can be decomposed into sequences of these partial state update blocks h sub I of x, which themselves can be decomposed into gi and fi. So this is the structure of a cadCAD model. And when you, in a way, the power here comes from the fact that no matter what it is you want to represent, this mathematical language is still very rich. It allows you to basically represent whatever it is you want to represent without loss of fidelity. You always lose some fidelity when you represent, but with control over the loss of fidelity in a meaningful way, you're making choices. And then cadCAD itself turns these states and partial state update blocks into trajectories. So Emanuel, I'll let you continue, but I really want to emphasize the fact that everything that you think of as modeling is really happening in declaring the state and the dynamics. Once you've done that, cadCAD is effectively automating for you, turning that into trajectories. It makes data.
Yes, exactly. Yes, so then, continuing, we have the trajectories that as I said, a trajectory is the sequence of all the produced states that were produced by the dynamics of your model, and then all of the states, all of the individual states that belong to a trajectory, they also belong to the same state space, right? Meaning that the dynamics of your modeling cannot make your trajectory to go outside of your state space. Like your states cannot become something else entirely, like the attributes of your state, something like that. Okay, so moving on, here on this next section, we say determination conditions, meaning, well, I have the dynamics and I have an initial state, so I have the potential of building a trajectory, so I can apply the dynamic on top of states, but I have to have a way to stop the simulation, right? There will be a time where there is enough, that the trajectory is big enough. And so I have two choices here. I can either use a maximum iteration. So for example, I want to a trajectory of size 200, for example. So I will do 199 steps of the simulation. Or I can use an absolving state. And that is, if the last state that I produced by applying my dynamics obeys some sort of predicate, some sort of attribute, if it is true for some property, I stop the simulation. So that's basically what this section is saying, all right? Those two ways of stopping the simulation and saying, I'm done. Okay. And then the last step, that is that was the newest section, the newest addition to our formal specification, is the parameter sweep. So basically, the parameter sweep says, well, what if I want to do a different run of the simulation, okay, but only changing slightly some parameters of my dynamics, of my set of laws. So that's what a parameter sweep basically is. So I can parameterize my dynamics, my laws of motions, for example, and then I can, from that, have very different trajectories based on slight change to the dynamics. You guys know what I'm saying? So, for example, if I have a set of laws, a dynamics, but if I parameterize that dynamics, for each parameter of the dynamics, I can produce a different trajectory, okay? And I can do the same on the initial state, not only on the dynamics. I can parameterize the initial state and then produce a series of trajectories, each of those trajectories from a different initial state that are slightly different from one another, for example. right? So I sweep through the parameters. And that's basically what this section is saying.
And this is a really important addition to the specification, though, because it ties fundamentally to what cadCAD's used for, right? cadCAD is not just complex adaptive dynamics, it's computer-aided design. So the name. What do we use it for? Computer-aided design. What does that entail? It entails running sort of sensitivity testing type experiments where we look at the co-fitness of behavioral assumptions with mechanism designs. So we quite literally sweep wide ranges of initial conditions, policy designs, behavioral policy designs, mechanism sort of like rules, laws of motion designs. And so in order to actually hone in on a design and to understand that design's sensitivity to your assumptions about behavior, you actually have to do lots of parameter sweeps. So at the end of the day, if we couldn't really formally understand how to support parameter sweeps, we weren't really building the tool for its use. And so for all of these mathematical objects, we care about more than just an instance of a trajectory. We care about trajectories we care about comparing trajectories based on variations in specific metadata. And so the whole construction of a parameter sweep is about ensuring that we have scientifically controlled experiments allowing us to compare trajectories, or in a maybe an intuitive way to think about it is we create a bunch of alternative universes and compare them side by side. But if we want to do that, then we need to keep track of what the variations are between those alternative universes. Otherwise, the data that it produces isn't super valuable from an engineering or from an analysis perspective. So that kind of brings you to the end of the spec, but Emanuel can kind of give us some comments on implementation and then actually dive into the last section of today's presentation, which is about the actual implementations of this. If there are questions on the spec, though, maybe we can take them before we dive into the code.
Yeah. Now that I'm going to talk about implementation, maybe we can open for questions now. Any questions?
What you just said about parameter sweeping?
Yeah.
So I think this is not any weakness in cadCAD, but I think the token engineering community in general is probably not aware of proper parameter sweeping. For instance, like the bifurcations in the logistic equation, a person using a cadCAD model to look at that probably does not understand the gradations at which they need to test their parameters. So, when you have chaotic dynamical systems that are very, very sensitive to small changes in the parameters, most people are not aware that those things even exist. And so they might try like 5 different values, and they probably need to know that even small changes can make drastic changes in the behavior of the system.
Yep. You are 100% correct. And in fact, I mean, this is a point of, let's say, like, immaturity in the, at least the token engineering space, because if you're coming at this from a traditional engineering space, you already have some existing common knowledge about what kinds of phase transitions or risks or vulnerabilities exist in the category of complex system you're analyzing. Like often, in fact, a CAD tool that's more specific will have a lot baked into it to help you do that. Whether it's guidelines or whether it's standard tests or whether it's default granularities, like a lot of this stuff is managed at the level of tooling plus common knowledge in a domain-specific sense. I think one of the real challenges is that token engineering attacks a much more fundamental space where you can't really pre-code that as much. You have to have a deeper understanding of the system that you're analyzing, and you need a slightly longer workflow sometimes to flush out or uncover or literally search the space to find the transition-like regimes. And to be fair, like, Danilo has done a lot of work on this in our practice at Block.Science, and so it might be prudent for a future one of these calls for him to come talk about what we call the parameter estimation under uncertainty, where there's a couple of related workflows that actually use this capability to actually find things like transition points in these complex systems. And so you're totally hitting the nail on the head, but I think it's actually more about the maturity of the practice of engineering systems that have these sort of chaotic dynamics, and less a maturity of the tooling itself. And part of the presentation of this and the addition of this to the spec is to make sure that the cadCAD supports it. When people are ready to do that, the tooling is ready to help them.
Yeah.
Would you have an example of a one of those transition points, like a Web3 example or something from modeling that's been done that you've seen?
Yes, but the truth is that I can't get into it easily because they tend to be high dimensional, at least in Web3. In the non-Web3 examples are comparatively easy. Even the predator-prey dynamics, if you sweep them, you'll find rules under which the systems frequently die because let's just say the predators need too much food relative to the prey's growth conditions, and the thing just collapses because the predators eat all the prey, the prey all die out, then there's no prey for the predators to eat, and all the predators die. So you have collapse conditions versus with high probability of collapse conditions versus a switching point where the system is capable of getting into mostly sustainable orbits. And then there's even because it's an absorbing barrier that there's still a gradation over which the probability or the time scale in which the system collapse varies. And so you can build out models like that. There's also some, I guess, probably more canonical high sensitivity models where any minor variation results in huge differences in trajectories. I don't have a good example coming to mind, but there's Lorentz equations, I think, have this property. But there are mathematical objects that just have really heavy parameter sensitivity.
I have a really quick example, if you don't mind me sharing it.
Yeah, please.
Because I think that, like you said about the maturity, I think all token engineers should know this, which is a very judgmental thing to say, so I apologize. If you look at just this, it's kind of a classic of changing the alpha value. If you explore the alpha value, you'll get very different changes in behavior. So this should be x sub n. Just generate the next term by multiplying whatever you pick for this value, multiply the previous term, and then 1 minus the previous term to generate the next term. And it's a really classic chaotic dynamical system.
Nice. I like it.
Awesome.
You want to take I almost took a screenshot, but it was a little fuzzy. I would drop that in the cadCAD community call for the image for future reference. But yeah, and actually, to be honest with you, this is one of the main challenges too, is just building out not just the tool knowledge, but the domain of practice that uses the tool knowledge, right? As long as we're doing complex adaptive dynamics computer-aided design, that's a practice. cadCAD is a tool, one of many that can help you with that practice, but cadCAD's emphasis is on generality. So you can use it long before you have any idea what medium you're going to implement in, or when you're implementing across multiple mediums, or even as a tool for being the substrate between multiple models that are implemented in other modeling frameworks. So there's lots of cool stuff that we are brainstorming with using cadCAD alongside other tools. Someone mentioned Token Spice earlier, which is great if you know that you have an EVM, and if the scope of modeling is very specifically about the EVM's affordances and a mechanism design where you are testing the same concepts, right? All the concepts in the spec might exist, but that your dynamical system is administrated by an Ethereum virtual machine, then there's a lot of benefit to having tools that are specialized to modeling Ethereum virtual machine. It's just that cadCAD is comfortable modeling that maze logistics equation as it is comfortable modeling something like a smart contract for a Uniswap or whatever. So it's important to understand the tool itself is not the same as the practice of engineering, and you use the tools that fit the problem at hand. Anyway, so maybe too long of a tangent. I want to give Emanuel time to talk about the implementation updates, though. So maybe we can jump to that.
All right. So I think our time is close to the end, so I'll try to speed things up. Basically, the parameter sweep is the last section of the firmware specification. Okay. This section here, implementation observations, just some notes that I took when I was like writing this parameter sweep with Zargham about what would happen when that mathematics becomes a programming language. Okay, because here's the whole work behind this whole research work behind the Julia implementation of cadCAD is actually like seeing what parts of the formal specification were missing, and then writing those parts that the Julia engine needed, and then transforming that mathematics into software. So I like to call that engineering the mathematics, right? So there are various ways of engineering this kind of mathematics, any kind of mathematics really, because those are two very different universes with different particularities. So you can like engineer that mathematics like on a more obvious way, on a faster way, or you can just do it slower, always thinking about performance. And the Julia implementation was born, the idea of it, with performance in mind, because for some like long running and very, very big simulations, the Python engine is slower. It's kind of slow because the Python language, I think you guys know that it is slower than most languages that are used on computers, on scientific computing, on the scientific computing universe, because it is a dynamic typed language, and because of that, it is not as performant as, for example, Julia. Okay, so I'll just bring up some slides here. So just to give you an overview of that research effort. So basically, this is a picture that I like very much that helped me a lot when I was writing and trying to understand the Python source code and writing in the beginning of the writing of the Julia source code. This is basically the very core of a cadCAD engine, right? We have a state, and computationally, a state is an aggregation of variables, all right? And then we apply over that state some policies, and those policies, they are aggregated. The result of those policies are aggregated into what we call a virtual state, okay? And that virtual state gets fed to state update functions, right? And those state update functions produce another state. So that whole purple area, this whole purple area is a partial state update block, okay? And a collection of those partial state update blocks is what we call a pipeline. So basically, in one time step, we have one pipeline. Basically, that's how that works. So as you guys can see, now that we're talking about software engineering, the majority of the simulation time is actually spent doing the policies and doing the state update functions, right? And because of that, we had to find a way to accelerate this portion of the cadCAD engine, okay? So basically, the Python version of cadCAD is the first version of it, the first one that was written, and it is the default one for any simulations that we do at Block.Science, right? So it has advantages and disadvantages, as everything else in software engineering. As for the advantages, we have no type restrictions, right? Meaning that those variables here of the state, they can be of whichever type that Python can come up with, okay? Meaning built-in types like an integer, a float, whatever, or user-defined types like a class or a data class or whatever that the user defined on the system model, okay? We expressly talk about types here because there was a first try of accelerating the Python version of cadCAD through Python, but it demanded a lot of type restrictions, and it was very bad to impose type restrictions on the system modeler, because I want to make a state with my own classes, so how can I restrict that? Anyway, another advantage of Python is the extensive scientific computing ecosystem, right? There is a lot of scientific computing libraries. I think everybody here knows about them, like NumPy, scikit-learn, all of that. Those libraries, they are used by the system modeler together with cadCAD to do their simulations, right? And maintenance, because Python is a very easy language to learn, is a very easy language to advance in, and a very easy language to program in, okay? At least in comparison to other more low-level languages like C++, for example, right? So the maintainability of the software on the long term gets facilitated because of Python. But there are disadvantages, like the Python runtime, mainly C Python. It is lower than most of other languages, okay? And even more, that the Python is by itself a slower language. The cadCAD engine, and we discovered that through profiling a lot of system models, most of the time the engine spends moving memory around. So it allocates memory and disallocates memory and copies memory from one portion of the heap to another portion of the heap, okay? So I don't know if you guys are familiar with that nomenclature, but basically every process on an operating system, it has two regions of memory. Every process, doesn't matter. Doesn't matter if it is Google Chrome, it doesn't matter if it is Discord, it doesn't matter if it is cadCAD. So it has a stack and it has a heap, okay? The majority of the objects, mainly the ones that are created by the user, on a Python program, they are allocated on the heap. And because of that, heap allocated objects are much slower than stack allocated objects, right? So all of the states from a cadCAD simulation in Python, they are allocated on the heap. And because of that, when I try to read the previous state and when I try to write the next state that I just produced, I am always operating on the heap, and that makes the simulation slower, basically. So now we have our work in progress. It's not ready yet. I really hope, because I'm very excited for it, that it's going to be done as soon as possible. So we chose to do it in Julia because Julia is, although it is dynamic, in high-level language, it is compiled. And one of the reasons that the Python language is kind of slow is because it is an interpreted language. So what Julia does is, and we call as all Julia packages are called something.jl, we call it cadCAD.jl. So the whole point of cadCAD.jl is that the library gets compiled before distribution, right? So the process of pre-compiling Julia code, the Julia compiler does some optimizations, all right? And those optimizations help accelerate it on very long running simulations. So the promises of Julia are that it approaches the speed of C because it is compiled through LLVM. That is, LLVM is a framework of compilers, of C and C++ compilers. And through Julia, because Julia has very strong metaprogramming abilities, we were able to create immutable state updates, meaning the states that in Python are dynamic dictionaries that get all scattered through the heap. Now, the states are very tightly packed pockets of data that get all just very close together on the stack if the state is small enough, or if your state is too big, it goes to the heap, but it goes packed together. All of them packed together because they are immutable. So because the states now are immutable, now the compiler of Julia knows that I am going to need exactly this amount of bytes for all the states of the simulation. Because now it's predictable, all right? So because it's predictable, I can stack them all, even if I need to use the heap. So it's faster, right? I don't have to go jumping around the heap searching for the next state or the previous state. I know that my previous state is just on my back. So it gets faster. Now, about the types, of course, there are no type restrictions on the system model if I am doing a pure Julia system model. But our ambition is that we make the Julia engine, all right, read and execute Python system models in order to make that transition from cadCAD to cadCAD very seamless, right? Of course, a Julia system model is going to be faster than a Python system model, or both with cadCAD, but even though very little would have to be changed from cadCAD to cadCAD if the system model stays in Python. So that's our main ambition from now on, after stabilizing a little bit more the engine. And as for maintainability, also, Julia is a high-level language, so it doesn't. It's not worse than Python on the long-term maintainability of the library. It also has a very extensive scientific computing ecosystem. It is not as big as Python's because Julia is a lot newer. It's a lot newer language. But what people do is that people create wrappers around very famous Python libraries like scikit-learn, TensorFlow, for example, to make use of Python libraries in Julia, all right? And of course, there are also native Julia libraries like DataFrames, FluxAL for deep learning, and Plotly for plotting. So the person who chooses to make the system models completely in Julia is not going to find himself on a desert without accompanying libraries. So the main disadvantage of Julia is that, and basically is that the ecosystem, the scientific computing ecosystem, is less developed, less extensive than Python's. So our main goal for the future is to make the Julia engine see and understand Python system model to make the transition from Python to Julia more seamless, and to give acceleration to those who do not want or can't learn Julia to make cadCAD simulations. You know, like there may be some data scientists that only know Python and do not want to learn Julia. So we want those people to be able to use cadCAD. And there is just to finish, a very strong advantage of Julia. That's basically one of the most, one of the biggest roadblocks that we just finished with Julia. That is, parallelization of the engine is very, very easy. Because as you guys can see here from this picture, the policies here, they are stacked on top of each other, and the state of the functions, they are stacked on top of each other. That's not it's not random. That's because we can parallelize under some conditions the application of those functions. In Python, this is very difficult, and it is what we call a process-based parallelism. But in Julia, we can do this, and we did that with a thread-based parallelism. So that's going to make the simulation even more performatic, right? So there are some differences, more differences between cadCAD and cadCAD. I don't think we have time to go through them. but basically the way, so very fast, basically the way that we do states on Python is a dictionary. On Julia, it is we through metaprogramming by using a immutable struct. The way we do system modeling in Julia is through a toml file that configures the experiment, and then we do the language objects on a Jupyter notebook or on a script, whereas a Python simulation is everything is on a Jupyter notebook or a Python script. That's the main difference. And of course, the distribution of the package is actually where they are more similar. In cadCAD, the distribution is through PyPy, and cadCAD.jl is going to be through the Julia registry. The difference is it's going to be distributed, pre-compiled. So that's basically it. Any questions?
Do you have an idea of how much faster Julia would be than Python? Is there?
We have to do. Yeah.
Go ahead. How's that?
Yeah. We still have to do benchmarks. That's our next logical step, right? Before making, because here's the thing: we have first to compare cadCAD in Python to cadCAD.jl on a Julia system model to cadCAD.jl on a Python system model, right? My hypothesis is that cadCAD.jl with a Julia system model is going to, and then cadCAD.jl with Python, and then pure Python. But we have to stabilize the engine first and then benchmark on a very different series of system models to really know if the hypothesis is correct. That's going to take a while.
Cool.
So I have a question for the group, and that was, from a content perspective, is this interesting to you guys? Because what we're really giving you is updates from what are, like, this is some of the stuff that's going on in core tech. So like Block.Science is still largely funding the development of cadCAD, even though it's open source. We do have funding that we've gotten through Gitcoin, and that we're like, Katoya, who's on, has been doing a lot of work with some other team members, community members, to figure out how to, fund more community-driven work. But I'm kind of curious about people's level of interest in this part of cadCAD, right? This is building, expanding, and refining cadCAD itself. Rather than, we have education and outreach, and we have the development of the infrastructure and the organization, et cetera. And I'm kind of, sorry, I'm still talking. I'm trying to understand what people's level of interest are in presentations on the core tech, or whether, if this is way over your head, then maybe we'll start a separate call for updates on this stuff. But if this is really interesting and you think it belongs here, then we'll try to make it so that every so many times we have updates from the sort of core development on cadCAD itself as a community call topic.
I could jump in. So, from my perspective, I think it's actually extremely relevant, kind of like what Octopus was saying, knowing these details, this level of detail, is pretty important for someone who's using cadCAD on a daily basis to build models, because you actually should know the tools that you're using and the limitations and the features and things like that. And then as for the Julia implementation, that also seems highly relevant for anyone who's running into issues with performance. I think it's good to know that there's work being done to improve it, and I'm sure that the people in this call and elsewhere that are using Python would eventually love to use a faster version if there was a Python implementation of Julia. So it seems super relevant to me. And also, I thought it's well explained and clear, in my opinion. I didn't think it was too heavy. It's complicated, big words, but I think it was very well explained. So not giving myself too much credit.
You've been well prepared.
And there's also just like a broader, like I would say, legibility gap. I mean, like cadCAD is created by and for pretty hardcore researchers. So like one of our other gaps is just like really figuring out how to build out this community and help get people engaged at different levels of detail. So, I mean, this being the community call, I know we're 10 minutes late, but I'm not here that often. I'm usually busy working on stuff. I tend to avoid being in out, and maybe it's hard to tell, but like I prefer to kind of be at brass tacks rather than like working on stuff rather than on calls. But obviously, it's helpful to do this kind of thing periodically. There's a lot of room for us to improve our well, I mean, Discord's not super active except for during these calls. We have working groups. The working group work is happening, but I think that there's a lot of room for community development around cadCAD. And I'm like really open to thoughts about like how people want to participate, like what participation should look like. I don't know if you're not familiar, there's 3 official working groups: Core Tech, which this is the byproduct of; Infra Admin, which is really more about keeping all of the services, and like we have Discord, we have GitHub, we have a forum we don't use much anymore, but we could use more if we thought it was helpful. Even including infra admin includes actually setting up a legal nonprofit organization, which is an undertaking Katoya has been leading on in order to improve stuff. So anyway, broadly speaking here, there's a lot of opportunity for us to like have more contributors, have more engagement, and I'm open to, or like looking for people to sort of step up and say, hey, these are the ways that I would like to get involved, or if you know other people who want to get involved. We're trying hard to make that a little easier, because I think the natural byproduct of building a pretty technical tool by really technical people, especially when its value proposition or even its use is growing well beyond that group, lends to some gaps in at least in the education and outreach, if not in other domains. So anyway, just kind of brainstorming.
Yeah. One thing I'd like to just sort of highlight, it was like a subtle thing, but I think it's pretty important, was I think there's a lot of value in doing these talks on cadCAD at this level, because it's conveying the design philosophy of our approach in building these frameworks, where it becomes clearer when we're talking about this in comparison to something like Token Spice, right? Where it's like cadCAD is really useful when it's like you're doing a sense-making process about the thing you're trying to model, right? You don't know exactly the thing you're going to do. Where like in Token Spice, if you already know that like an EVM is important to you, you probably have a pretty clear idea of the thing you're trying to build. Whereas in cadCAD, you're using the tool to sort of get your thoughts down on paper, and then eventually in a model. And playing with the model sort of reveals insights about the system you're trying to model. And that sort of is imbued across a lot of design decisions here. And so I think it's important to have these talks, because if people want to contribute not just directly to the engine, but into additional utilities in sort of third-party repos that facilitate using cadCAD, being behind that design philosophy, I think, is really fundamental.
As a pedagogical presentation structural thing, I think this version of this talk would help to map to something concrete, because I think you have the 2 extremes of the boot camp level demonstration, and then you have this, and something like, if you're going to present it as a generalized dynamical system, and then you can go through something really simple like the robot marble system. Okay, what is the F sub T? What is the set of legal actions? How might that change? I think this is a problem like in all engineering STEM disciplines, that we have the nothing between heaven and earth. We have complete abstraction, and then the nuts and bolts calculation, and very little very little to connect it to. So
I think that's
that would
right.
be my thought.
Yeah, so I mean, back to the call to action though, that's one of the lowest hanging fruits, I think, for people who have made it to orbit, somewhere between heaven and earth, practically, for whatever reason they've been around. Like, we try to build those. Like, Marcus wrote The Robot in Marbles. He and I worked on that. There's a handful of other examples of cadCAD floating around in the cadCAD demos, which were created for that reason, albeit not disagreeing. We probably should have planned to present some of that to Anchor, but I think there's a big gap also here in just the terms of how this community builds out around that level, because Octopus, I think that's the level that most people enter on. They might be interested in the implementation details and the performance, or they might be interested in the theory and the design principles, but I think most people enter through the layer that you're describing.
And I'm just saying, I'm agreeing with you. I'm not saying it's a criticism of this particular talk to this particular audience. I'm just saying in general, in all STEM, all token engineering, there is a real problem with not making the bridges explicit between the theory and the practice.
Yeah, I agree with you. That's definitely true. We just got to try to figure out how to be even marginally better.
Yeah. No, it was really a wonderful presentation. I found it really intriguing. And I had I gained a lot of value from it, so I really appreciate the opportunity to come.
Well, thank you for coming. I mean, I think we'd probably wrap up. We're about 15 minutes over. I can field questions for another 10 minutes or so if people want to stick around, but a hard stop then.
Well, I'm not going to let this opportunity go, so I want to give other people a chance to ask before I ask some more questions.
I'll stick around and listen.
I saw that cat unmute, but I can't hear him. I'm not sure if he's trying to talk.
Oh, I want to ask a question, but I was trying to think how to word it. I guess I really like to be able to see the theory, like the mathematical theory behind the cadCAD system and how you guys bridged it over to defining like you took hard math theory and made it a abstract thing that could be implemented in different programming language contexts. And I find that transition from a mathematical formal specification to a hard code implementation, I find that really, really cool. And so I found some great value from seeing how you guys did that.
So one thing you need to understand, though, is it happened kind of in loops. So like much of engineering, the intuition started from the fact that I have a pretty strong background in dynamics control, signal processing, and algorithm design, but I didn't have the tools to replicate the mathematical objects that I was writing on whiteboards and in notebooks. And we implemented the first version of, actually, we implemented a bunch of these sort of token engineering style generalized dynamical systems in an ad hoc way in pure Python, which before that I used to do in MATLAB as a graduate student and whatnot. Then cadCAD came about because Joshua Joti was working for Block.Science, and he had the lead task of figuring out how to basically take what we were doing and kind of distill it into a framework. And so the working version of Python today is a manifestation of him working from the practical to the software. So from my math intuition to my hacky Python simulations to Josh's frameworkization of that to us iterating using that until we got to the point where we had enough clarity to go all the way back to the math framework and really say, what is it that we're really doing? And then that math framework, having hardened through practice, became something that Emanuel could take and almost start from scratch. Be like, okay, let's not worry about how we implement it in Python. Let's just take the really strong, well-articulated math object and implement it in a performant way from the beginning. And so as we get into this Julia implementation and the acceleration of Python via some some language translation. What we've really done is gotten back to the math object and then gotten this implementation moving. We didn't jump straight from the math to the implementation. If that makes sense?
Yeah. Much like the rest of software engineering, it has to naturally evolve over time to eventually come back to the beginning to have a strong start for new projects.
Yeah, but I think it's more than just, so one of the things I see in software engineering or in a lot of building of things is that the evolutionary process has not enough negative design or enough synthesis and rebasing. Because what we basically stopped and said was, okay, what did we learn? And now if we were to start from scratch, in a sense, what would we do? And that gave us the opportunity to do better in a way that was sort of discontinuous. And I think that if you just follow a purely evolutionary model, you get things that get kludgier and kludgier over time because it's difficult. It's actually really difficult sometimes to step back, lift out the fundamental concepts, generalize away the details, and look at what's left, and then go forward again with application, but after kind of stripping away what I would call the non-critical elements. And the math spec for this specification was actually an exercise in saying what's critical, not what's there, but what's critical. And that was leading to the performance improvements in a way that just keeping things because they're there or defining the specific. If we had written the specification by going through the Python cadCAD code and said, oh, this is what it does, we need to do that in Julia, we wouldn't be anywhere near the same place we are by essentially setting the implementation aside for a moment and merely asking, what is this abstract math instance of a model?
Mm-hmm.
So the one thing about cadCAD that I'm really curious in the design process, kind of the rationale of where policy functions, like why you chose to go through policy functions as an intermediary step to state functions.
This is a really critical design choice. So I'd be thrilled to talk about that. So here's the thing about reality. It never works the way that you think it's going to work. And so if you want to deal with designing anything real and you're not just like telling a story, then you have to be able to encode uncertainty, encode your knowledge of your lack of knowledge about things. So the formal separation between g of x and f of x comma u is about breaking in your mathematical object apart and really treating differently the things that are declarative from the things that are like modeled or discovered or unknown, so that you can do different kinds of assumptions about them, so that you're not bound to treating them symmetrically. Because in practice, it's actually really important to say, I know this, or at least I have control over this. It is controllable. Whereas the thing that goes in policy or in behavior is by definition out of the scope of the system you're designing. It might be part of another system. It could be a human decision maker or the outputs of another piece of software. But in a systems engineering context, you always have interfaces. And I know what my thing does, but I really don't know what's going to come over the boundary. And so by taking G and saying we can use G to encode information that comes from, outside the thing I'm designing, or at least, comes across this interface, and using F to declare the stuff that is like, I get to decide how it works and declare how it works. We break apart the sort of implicit requirement that those are treated the same way. And so it's actually very much born of practice. It's that if you make that mistake, there's almost no coming back from it. And so we make it canonical or for the first order in our representation of these dynamical systems.
So it actually is policy and like in the same etymology as police, that you have an outside force that is coming that you don't really,
Yeah, actually that's interesting because I hadn't thought of that etymology, but the truth is that policy, whether it's in control theory, control policy is the decision-making operator. In economics, like policy making is this thing that you construct and impose upon others. So like literally the etymology of policy is outside, and the mechanism is like endemic to the thing it's part of the thing you're designing. And you have to design for a gestalt that's comprised of both the thing you're making and the external thing it's interacting with.
So if you are doing a crypto simulation and you want to take into account regulators, they go in the policy function.
Yes, assuming that the regulators are taking actions. But interestingly enough, you might design a system where the concept of the policy the regulator's making is a mechanism, where you take its adherence for granted. So it's, again, it's very much a framing thing. It's a pretty general modeling language. So when you define the perspective of the system you're designing, if you are designing the regulation, you might actually put the regulation in mechanism and the behavior of users with respect to that regulation in policy.
Sure. So policy is whatever is essentially external.
Yes.
Understood.
Or in another way to think about it is they encode boundary conditions. Or maybe an even better way to say it is that the admissible action set defines the boundary condition rules, but then the input coming over that boundary condition is the thing that's coming from the behavior, from the G of X, from the policy layer. And to be fair, we've been like messing around with terms. The semantics are tricky. Policy is a loaded term. So like, you know, we've also discussed it as just white box and black box recently. Because black box encodes, we don't know how or why, it just happens, and we can still make it a heuristic. It doesn't have to be like a black box machine learning model. But as an engineer, the white box is the physics that's under our discretion, and the black box is some behavior that we're modeling that's representing something out of our control.
Sure. The problem is black box has come to mean there's too much linear algebra for me to comprehend the algorithm.
Yeah, that's fair. Well, and I mean, this is an issue where we're in a space where semantics are tricky. We can use existing semantics to call to mind or analogize to things, but in some ways we also might want to avoid using the existing semantics because the terms are loaded. We're working across multiple fields, and so the implications of policy, depending on which field you're coming from, in control theory, like the control policy is literally called G of X, like at least in nonlinear control, right? And it outputs U. So like we borrowed the first etymology from control theory. But like, is it, is that right? I mean, no more than any other interpretation. It's the mathematical object that is good at representing the phenomena that we're after. So in fact, I would argue that some of the semantic choices are something that I'm open to. I continue to be open to discussing because I feel like they can sometimes cause as much issue as they resolve.
Mm-hmm. No, I mean, there's no free lunch, so it's obviously a very useful tool, and when it's misused, that's clearly not your fault.
Sure.
It is a wonderful tool.
I think your question though about the policies, about the G of X separation from F of X, actually digs at almost the only thing that differentiates the generalized dynamical systems from the way that we currently think about dynamical systems, besides the general spaces, the record objects. By breaking these two things apart, or we're sort of doing a factorization that really doesn't lose anything, but it still adds some structure. Because if I say that the G of X has codomain U, but that I'm talking about the set that this can lie in. So it's like U of X, the set, the codomain of G of X is like part of the mechanism design F of X. So you're doing something kind of nuanced. You're creating another operator that represents the set of things that can be done. And that is, at least in my feeling, really important for understanding the set of things that can happen. And the robotics equivalent of this, or the place that this appears in robotics naturally, is when you're looking at things like, I'll use an example, like a robotic arm. A robotic arm has very specific actuators, ways in which it can bend and move. And thus it has an admissible action space that's afforded to it by the specific actuators that move the arm. And what this means is that, conditioned on those specific rules, there's a very specific set of configurations the arm can take, like the space of reachable alignments of the arm is called a configuration space. And so when we use the term configuration space, what we're really saying is that in any of these mechanism design problems, once you combine the physics part that says how things move with the sort of range of motion of all of these moving parts through the admissible action spaces and the physics together, you get configuration spaces, or shapes of space, manifolds that represent what can happen, and then we can worry about behavior inside of that structured space.
Yeah, so that's really helpful to me. I appreciate your elucidating that, because what's bothered me for a while is there's no mathematical necessity to the policy function, but it's a philosophical thing that emphasizes a particular viewpoint, and that makes a lot more sense to me.
Yeah, it is canonically unnecessary, though, in the same way that any of the mathematical structures that you find in like a signal processing and controls, like they impose, like they represent very general mathematical objects, like all possible ways in which some certain fields can change, right? But then you have to pick a canonical form, and the canonical form is itself just one of many representations of the same mathematical objects. And at least in my experience, the canonical forms have UX properties. They exist in that form to standardize how people think about it and talk about it, to emphasize some things over others, to help with the use of those mathematical objects to make things and to evaluate things. And that's where the whole computer-aided design thing connects back into these choices.
Yeah, there has to be community consensus about some things. So, well, that's really helpful to me. I really appreciate your taking the time to give your perspective on that. Thank you very much.
No problem. Thanks for listening and caring, because I feel like this in particular is something that I'm not sure most people even like care or understand enough to ask about, because it is actually pretty central to, at least from the design choices perspective. It's opinionated, and it's opinionated for a reason.
Mm-hmm. Yeah, I think it goes back to like actually understanding the tools that you're using, and people probably wouldn't even think to ask these questions or realize it's important, but it actually matters a lot. So yeah, so thanks a ton for that explanation. I think maybe you got to run too, and we're quite a bit over time. So thanks to everyone for sticking around. It was an awesome presentation. I hope everyone learned a lot, and yeah, the recording will be up sometime later this week. If you want to check out, circle back and recover any of the topics. So yeah, I think that's it. I'll let everyone go. Have a good day / night, and thanks Emanuel and Z for presenting. Oh, can't hear you actually. It might just be me. Oh, okay. Maybe it was just me, but